In 5.5, we learned to divide polynomials so that we could start to factor polynomial functions, but you should have noted in the homework section they always had to give you a zero or give you a factor in order for you to get started. In 5.6, we're going to discuss one of the tools that can be used in order to figure out which are likely candidates to use synthetic division to determine whether or not they're factors. So if you haven't been given a zero or a factor, where should you start? And the answer to that is the rational zeros theorem if you're doing it by hand. Now, the rational zeros theorem is a theorem that basically tells you what the rational zeros of a polynomial function might look like. So I'll start with an example. Oh, well, I forgot to talk through my summary, but I'm almost done writing it down. Give me a second. Okay, so we're going to talk about what that looks like. We're going to talk about how that helps you make a list. We're going to do a couple examples where we check the zeros against the list, but by the time we're done, we're actually going to be using a graph to check against the list, which is much, much faster. So I'll sort of evolve this as I talk through it. So the rational zeros theorem says if there are rational zeros, it doesn't guarantee that they exist. The zeros might be imaginary, they might have square roots, which would make them irrational. Rational means it can be it can be written as a fraction, which includes all the integers and all the nice decimals. So things like a quarter or 5/8, they can be written as a fraction, as opposed to, say, the square root of 2, which there's no way to write as a fraction. So if there are rational zeros, they're all going to be a factor of the constant term, the term on the end, divided by a factor of the leading coefficient. Now, in the simpler examples where the leading coefficient is 1, that means we've got a factor of 6. We're going to ignore the fact that it's negative, divided by a factor of the leading coefficient, which is 1. Fortunately, 1 only has one factor itself, so these are all going to be integers, the ones we produce, because we're going to divide them all by 1. So we're going to find the factors of 6, which are 1, 2, 3, and 6, and they all need to be divided by just 1. So when we produce this list, they're all either positive or negative. The rational zeros theorem does not specify signs for these solutions, these zeros. So plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, which is a total of 8 possible rational zeros. Now, the rational zeros theorem does not guarantee that any of these are actually zeros. It just says if there are nice zeros, if there are rational zeros, they're the ones on this list. The zeros could be imaginary, though, and so make sure when you're doing problems from a textbook on these that you read the instructions carefully, because it's quite possible they'll give you an example like this. It will have none of these zeros because they're all yucky. So make sure you read the instructions, or you can spend a lot of time banging your head against a wall. So my next example, where the leading coefficient is not 1, we're going to get fractions. 4x to the 5th plus 3x cubed minus 2x minus 14. Of course, all those numbers in the middle don't matter, because all the rational zeros theorem says is if there are rational zeros, they'll be factors of 14 divided by factors of 4. So the factors of 14 are 1 and 2 and 7 and 14. And the factors of 4 are 1 and 2 and 4. So first I'll take all these and divide by 1. I like to do this systematically. You can actually approach this any way you like as long as you get all 12. There's 12 different combinations here. Some of them are duplicates, though. I'll get to that. So I like to go systematically. I start with the 1 on the bottom. So 1 divided by 1 is 1. Don't forget to put that as plus or minus. So plus or minus 1. 2 divided by 1 is 2. So that's plus or minus 2. 7 divided by 1 is 7. So plus or minus 7. And then, of course, plus or minus 14. So when I take 2, I do 2 divided by 1. I'm dividing by 2. 1 divided by 2 is 1/2, which is new, plus or minus 1/2. 2 divided by 2, though, is 1, which is already on my list. I don't need to repeat it. It's already there. 7 divided by 2 is not on my list, 7/2. And 14 divided by 2 is 7, which is already on my list. So then I'll do the 4 on the bottom. 1 divided by 4 is 1/4. That one's new. Plus or minus 1/4. 2 divided by 4 is 1/2, which I already have. 7 divided by 4 is 7/4, which is new. And 14 divided by 4 is 7/2, which is not new. So now I have a list. This is actually 8 plus or minus, so 16 possible zeros. Going through that list might take a while. There are up to 5 of them will work. Although again, be careful about your instructions. I haven't actually checked which of those are actual zeros, so I have no idea. And I'm not going to bother checking because I copied this down out of the section of a book that just said make the list and didn't tell me to verify which ones are zeros. Now this one, x cubed minus 5x squared plus 7x minus 35, was from a section that said find all of the zeros. And since it's in this section and asking me to find all the zeros, I can assume that at least one of them is rational. So I'm going to make my list. Factors of 35 over factors of 1 is, let's see, 1, 5, 7, 35, all plus or minus. 35, that was a nice number for them to give us, for all that it's a little big. It's only got 4 factors, so 8 total numbers to check. Again, I'm very systematic, so I'm going to start with 1. I'm going to go up using positive numbers, and then I'll switch to negatives if I have to. Now, for reasons that I'm going to explain to you when we get there, technically, since this is 3rd degree, I only have to find one of these zeros using synthetic division, because my quotient will be, I'm explaining it now, my quotient will be quadratic, and I can use the quadratic formula for the last 2. It's a very good strategy. So I'm using synthetic division to see whether this one works. -4, -4, 3, absolutely not. -32, oops, 32. All right, so next is 5. No point trying 2, it's not on my list. There's no way 2 is a zero of this polynomial, because if it's 2, it's rational, and if it's rational, it's on this list. So 1, 5, 0, 0, 7, 35. Look at that. Found it. Only took me 2 of my 8 numbers to find one. It's 5. Now this is left behind. This is 1x squared and no x's and a 7. And I've got x minus 5 as one of my factors. Here, for x squared plus 7 to equal 0, x squared would have to be -7, which, since we all did chapter 4, we know that means x would have to be plus or minus the square root of -7, or plus or minus I square root of 7. These are imaginary, so in this section the instructions will say find all the real zeros, so these are not real, which means the only real zero is 5. Notice when you get to the last 2, doesn't matter if they're real or not. And this time I didn't even need the quadratic formula because it was ax plus c. I should say ax squared plus c. So I was able to solve it using square roots. If this were a trinomial that I couldn't factor, quadratic formula will verify whether the remaining zeros are real or not. So that's one I did entirely by hand. No, even if it were like 4th degree, I'd have had to keep going, but I'd have to find 2 of the zeros to make my quotient quadratic, last 2 quadratic formula. For my last example then, we will be using the graph in order to narrow down our list of possible suspects, which means I really should have opened Desmos earlier. Let me get it running here. Okay. All right, so here's my Desmos. For my last example, I'll be using -9 x to the 4th plus 3x cubed minus 30x squared plus 6x plus 12. All right. So y equals negative 9x to the fourth plus 3x cubed minus 30x squared plus 6x plus 12. All right. Now I wish I'd checked the answers in advance. This is a fourth degree polynomial, which means I'm expecting to find up to 4 zeros, and I see 2 of them. Oh, and both irrational? I have typed something in wrong. 9x. Oh, it wasn't supposed to be negative 9x to the fourth. It was supposed to be positive. Ah, much better. Okay. So, I can see right there, negative 2. Oh, this has 2 zeros over here. All right. So when you're looking at one of these graphs, these right here, decimal approximations, they're no-nos when we're doing this section, just because the whole point is to find them precisely using synthetic division. So we're going to take the ones that we can see that are nice. We're going to check to make sure that they're actually on our list. Anytime you use a graphical approach, you're doing approximations, although in this case, I'm pretty sure those will be accurate. But I'm going to use these zeros that I find. I'm going to do synthetic division in order to break down my polynomial so I can find the ones that aren't so nice. So I'm taking 1. Now, since 1 is always a factor of everything, 1 is definitely on my list. And then negative 2, well, also a factor of 12. So these are both on the list I would have produced. I suppose I could produce that list for you. But with 9 and 12, they both have quite a few factors. That would take a very long time. So instead of producing the whole list, which honestly doesn't matter to me, I know which ones I want. Why is this not ordering? There we go. Okay. So 1 and negative 2 are my suspects. I'm going to divide by 1. 9, 3, negative 30, positive 6, and 12. 9, 9. 3 and 9 is 12. It's 12. Negative 18. Negative 18. Negative 12. Negative 12, 0. So now I have a third degree polynomial, but never fear, because I also know negative 2 works. For this, because I've already found one of the factors, I'm not going to go back to the original polynomial. I'm going to use the quotient. Although I haven't put the x's in yet, I don't need to. I'm doing synthetic division again. So this is 9x cubed, 12x squared, negative 18x, and negative 12. But I'm going to divide it because the whole point is to factor out this polynomial. So this makes 9, negative 18, negative 6, positive 12, negative 6, positive 12, and 0. So now I have x minus 1, which was what I divided by first. And x minus negative 2 is x plus 2, which I divided by second. And the remaining factor is 9x squared minus 6x minus 6, which I could immediately stick into the quadratic formula, but these are all multiples of 3, so life is going to be much easier if I factor that 3 out. You know, I should have done that way at the top. I just realized. So this is 3x squared minus 2x minus 2, which is going to be a whole lot easier in the quadratic formula. Opposite of b plus or minus the square root b squared minus 4 times 3 is 12 times negative 2. It's going to be positive. 12 times 2 is 24. All over 2 times 3 is 6. So this is 2 plus or minus the square root of 28 over 6. 28 is 7 times 4. Square root of 4 is 2. So that's 2 square roots of 7. Which means I am looking at 1 plus or minus the square root of 7 all over 3. That's two real zeros there because there's no i's. They're irrational, but they're real. 1, negative 2, 1 plus the square root of 7 over 3, and 1 minus the square root of 7 over 3, which, quite frankly, we already looked at. The minus one's going to be negative 0.549. That was what we saw in our graph. And the positive one's going to be 1.215-ish. Those are approximate zeros, though. Now we know the exact answers, which most of you may not care. I care. Exact answers. Super nice. Welcome to Algebra 2. These are all the skills that you need for 5.6. So now you can get started on your homework. Good luck.